So if the slope of CM versus CL curve is minus 0.29 and the pitching moment at zero lift coefficient is equal to 0.15, determine the trim lift coefficient. Enter answer to 3 decimal places. So this is a very straightforward problem. Slope is given, and we are talking about CM versus CL plot. So CM in the y-axis, CL in the x-axis. The slope is minus 0.29, so it is negatively sloped. And the zero lift coefficient is 0.15. So zero lift coefficient means, sorry, pitching moment at zero lift coefficient. So when CL equals to 0, the moment is 0.15. So this CM versus CL plot will pass through this point, which is 0.15, and it is negatively sloped. We know it is negatively sloped because the slope is negative, right? So dCM dCL equals to negative 0.29. And it says determine the trim lift coefficient. So this is the trim lift coefficient. So what is the value of CL at the trim point? So you have to realize that this is a straight line. So its equation will be given by CM equals to some constant, let's say K, plus slope times the independent variable CL, right? So this is like y equals to mx plus c. And you need to find the values of the intercept, and actually the slope is given to you. So this is very easy. So you already have CM equals to K, and the slope is given minus 0.29 CL. You need to find the value of the intercept, and that we can easily know from this information. So when CL equals to 0, we know that CM equals to 0.15. Therefore, 0.15 equals to K. So the equation for CM versus CL is CM equals to 0.15 minus 0.29 CL. Now we would like to know the value of CL at trim point, and at the trim point CM equals to 0. So you can make the substitution. CM equals to 0 equals to 0.15 minus 0.29 times CL. So you will get CL equals to 0.15 divided by 0.29, and you can use your calculator to obtain the final value. Okay, when an aircraft side slips by -4 degrees, the value of the roll moment coefficient is 0.59. Calculate the value of the roll moment coefficient slope with respect to the side slip angle to 2 decimal places in units of per degree. So the side slip angle is equal to -4 degree. And the roll moment coefficient. So the roll moment coefficient is given by CL. Right? M is for pitch, N is for yaw, L is for roll. So this is equal to 0.59. Calculate the value of the roll moment coefficient slope. What is roll moment coefficient slope? So this is CL beta, which is the same as dCl d beta. This is what you need to calculate. So it's very easy. Again, just to help your thought process, you could make a sketch of Cl versus beta. So it tells you that when beta equals to -4, so on the left side, so let's say this is -4 degree, Cl equals to 0.59. So let's say this is your 0.59. So this is the point that is given to you. But with only one point, you cannot calculate the gradient. So you need to know, okay, you need to know that the other point is at the origin, because at equilibrium point or at the trim point, beta will be 0 and the roll moment coefficient will also be equal to 0. When the aircraft is at equilibrium, it will not be rolling, right? There will not be any side slip angle. So this is something that comes from the knowledge of the conceptual understanding of the roll stability. Yeah. Okay, so finding the gradient is very easy then. This is the line. Okay, so this dCl d beta is simply going to be the change in Cl. Cl is decreasing. Okay, so it's going to be minus 0.59 divided by the change in beta, which is 4. So you will get a number out of this. Again, you have a calculator, you can calculate this number easily. All right. Okay, so that is the numerical answer, but it says comment on the static stability of this aircraft, minus 0.1475. So it says comment on the static stability. Since this Cl beta is negative, it will be statically stable, right? So since Cl beta is less than 0, the aircraft is statically stable. So you just need to put the extra comment. So consider an airplane with the following characteristics. The tail volume ratio is given. So this is the VH. Tail efficiency is given. Lift slope of the wing airfoil. Again, I'm trying to help you. I have underlined that it is airfoil. It is not the wing. It is the airfoil. Okay, so this means if you want to calculate the lift slope of the wing, then you have to use the following equation. CL alpha of the wing divided by 1 plus CL alpha pi AR. Let me check something very quickly here. Yeah, and this formula is given to you in the formula sheet as well. The code is given. Location of the center of gravity, XCG, is given. Location of the aerodynamic center is given. The tail lift slope. Okay, so now this is not the airfoil, this is the entire tail is given. The wing span, the wing area. Find the value of the moment coefficient for the wing tail combination. So there is no any fuselage contribution here. Moment coefficient slope. So this is Cm alpha that you need to calculate. And this is what is also provided in our formula sheet, but it is kind of fragmented, like you are given the expression for Cm alpha of the wing, and you are also separately given the equation for Cm alpha of the tail. So you need to calculate them individually and then add them together. XCG over C minus XAC over C. So here XCG over C and XAC over C are given, right? C is equal to 1 meter. Okay, so X alpha L alpha W is not given. We have to calculate that. But these other two are given. So that's going to be 0.26 divided by 1 minus 0.09 divided by 1. And you calculate this CL alpha W. CL alpha W equals to, now I already wrote the formula there. And even when you do these things, in the exam, you should first write the formula and then you should do the substitution. If you just directly write the numbers and if it is not correct, then I have no idea what's going on and you lose all the points, because I don't want to spend 20 minutes just trying to understand your one sentence, right? That because I'm also under time pressure. You have to realize that. And in general, it's a good habit to write your solutions methodically and neatly. Okay, so CL alpha W, this we know is just going to be equal to 2 pi. Okay, that's the slope of the lift curve for an airfoil. So this will be 2 pi 1 plus CL alpha W, 2 pi divided by pi times the aspect ratio, which is B square divided by S divided by the area. So this is 2 pi divided by 1 plus, okay, you can put this in your calculator or you can simplify and then put the simplified expression in your calculator. 0.4 square divided by 184. So what you need to realize is this will give you an answer which will be in terms of per radian, right? This equation and even this CL alpha W equals to 2 pi, that is true in terms of per radian. So you'll get a number here, and that number is in terms of per radian. So you'll take that number and then you will multiply, with these two terms inside the brackets, right? So you will just substitute here. Okay, so you have a calculator, you can do that. So that will give us the wing contribution. Now we need to calculate the tail contribution. Again, you can refer to your formula sheet. And I think the tail contribution is also, so the wing contribution is equal to 4.72 times 0.26 minus 0.09. So this will give a number, and that many per radian is the wing contribution. Now let's find the tail contribution. The tail contribution is equal to CL alpha T 1 minus D downwash D alpha. Now we are given the value of the efficiency factor, which is 1, and we have the horizontal tail volume ratio 0.31, and we are also given the tail lift slope as 0.1 per degree. Okay, we have to be careful now. And 1 minus this slope, which needs to be calculated. So this slope is given by 2 CL alpha W divided by, but again, write this CL alpha T in terms of per radian. Now, okay, putting it in terms of per degree may also be correct, but since we are going to add it with something which is already in terms of per radian, see the Cm alpha W is already in terms of per radian. So convert this 0.1 per degree to per radian so that we can combine the two per radians. Okay, so you're going to get Cm alpha T equals to minus 1 times 0.31 times, now 0.1 degree can be converted into radian by doing this. So 1 degree equals to pi divided by 180 radian. So this will produce the value of the tail contribution in terms of per radian. So now you have the tail and the wing contribution. You can combine them. So you have Cm alpha equals to the wing contribution, which is 0.8024, and the tail contribution, which is minus 0.895, or whatever is the correct answer here. And then you'll get another number here. That number will be in terms of per radian. And you need to convert it into per degree. And to do that, you need to multiply by, what do you need to multiply by? I think you need to multiply by 1 over 57.3, right? You have to do the reciprocal of what you did when you wanted to convert. Okay. So whatever this number is, you can find using your calculator. You divide that number by 180 over pi, which is 57.3. Okay, or the same number divided by 57.3. So that will give you the answer in terms of per degree. An airplane has the following pitching moment characteristics at the center of gravity position. So there is so the information that is going to follow applies when the center of gravity is at 0.5. So you are given the equation now. This is not written in the best possible way, so you just have to rewrite it and make it more readable. So this is the equation which is given to you, and some values of the terms in the equations are also given. Cm0 equals to 0.05, and the slope is equal to minus 0.1, and Cm delta E, which is also slope with respect to the elevator angle, is minus 0.01. And you are given this equation, dCm Cg dCl equals to xCg over C minus xNP over C. So this information is provided, and you are told that later on the center of gravity moves to a new location. And at this time, the value of CL equals to 1.4. So that will happen later on. So in this situation means when the center of gravity shifts to 0.2 and the lift coefficient becomes 1.4, what is the elevator angle required to trim? So there is only one answer. What is the angle required to trim? All right. So obviously you are solving for this. This is the unknown. And it says elevator angle required to trim. Required to trim means the overall moment coefficient will be equal to 0. The value of CM0 is given to you. It's 0.05. CL's value is also given to you. What is CL? It is 1.4. Now for the slope, you should not put this value. You should not put this value. This will be wrong. Because that value is only correct when the center of gravity is at 0.5. From this equation, you need to realize that the slope of the moment coefficient with respect to the lift coefficient depends on the center of gravity location. So if the center of gravity has moved from 0.5 to 0.2, then this slope will also change. So you need to recompute the slope. And we'll come back to that. The Cm delta E is also provided. So you just need to plug in this value. Now in this equation, you should use your understanding that although this slope may change, although the position of the center of gravity may change, neutral point is a fixed point. It's not going to change. So to find the new value of the moment slope with respect to the lift coefficient, you need to first compute the value of neutral point using the information that is given when the center of gravity location is at 0.5. So we get minus 0.1 equals to 0.5 minus x np over c, which means x np over c equals to 0.5 plus 0.1 is equals to 0.6. So this neutral point is in a fixed location. It will not change when the center of gravity will shift from one point to another point. So now let's calculate the new value of the moment slope. The new value is dCm dCl equals to, the new center of gravity is at 0.2 minus 0.6. This is equals to minus 0.4. So now we come back to this equation. There will now be only one unknown. All the others will be known. So I'm going to rewrite this equation by substituting the values for the terms that we know. So since we are talking about the trim point, the overall moment coefficient will be 0 equals to 0.05 minus 0.4 times 1.4 minus 0.01 times delta E. And you just solve for this delta E. 0.01. Okay, and that will be the angle. So again, to emphasize this, I want to refresh something that we have discussed in the class. See, we had discussed, okay, that the elevator deflection is used to shift the CM versus CL or CM versus alpha, right? So if we have a plot of CM versus CL or CM versus alpha, this is going to shift for different values of elevator angle, right? And that helps to achieve a trim point at different values of CL, which may actually correspond to different value of the aircraft speed, for instance, or different altitudes, right? Which means the density will change and the CL will change. So one thing is that you can deflect the elevator and that will shift the curve. And we had also discussed that another way of moving this trim point is actually by changing the slope, right? So let's say we had a curve like this. You could change the slope. Sorry, you could just change the slope, and now the trim point has moved from here to here. And how can you change the slope? You can change the slope by moving the center of gravity, and this you can easily realize if you look at the equation for the slope of moment coefficient in the formula sheet. So the slope of the moment coefficient is a function of center of gravity location. So either you can look at the detailed equation and realize this, or even if you look at this equation only, it's clearly telling you that the slope depends on the center of gravity location. And actually this equation which is given here strictly applies only when there is a wing contribution. When the tail contributions are 0, then this is the equation for the moment coefficient slope with respect to the lift coefficient. So you should calculate the center of gravity location in this problem, not CM alpha. I'm not asking whether this will be stable or not stable. This is not the question. Okay. And where does this issue arise from? So we know that we want to put the center of gravity towards the nose as much as possible, because that will help to make the aircraft more statically stable. If you look at the equation for Cm alpha, it will become more and more negative as you reduce the value of xcg, means as you make the xcg more and more towards the nose of the aircraft. Okay, but when you do this, some extra moment will also be created, which needs to be overcome by deflecting the elevator. So there is a limit to which we may want to move our center of gravity forward, and this limit is basically set by how big the elevator is and how much it can be deflected. Okay. All right. So now let's read the question properly. An airplane has the following pitch moment characteristics at the center of gravity position. So center of gravity position is given. It is given, but we need to find its limit. Okay. So, and the equation is also given. The value of Cm0, the slope, and Cm delta E are all provided, and the slope of moment coefficient with respect to the lift coefficient is also given. So the problem statement is very similar to the previous problem. Now assume that during landing CL equals to 0.9. So CL equals to 0.9 during landing. And the maximum you can deflect the elevator is plus minus 30 degree. Plus minus 30 degree. So what is the forwardmost position of the center of gravity? This needs to be calculated. Okay. Now again, let's recall. If we are going to move the center of gravity forward, okay, towards the nose or just in the positive x direction, then that will make the aircraft try to pitch down, because the lift is created at the wing, but now the distance between the lift and the center of gravity has increased, so the nose down moment, pitch moment, is going to increase. So this needs to be overcome by creating the moment in the opposite direction, right? So in this direction. To do that, we need to deflect the elevator downward. No, not correct. To do that, we need to deflect the elevator upward. So when we deflect the elevator upward, then this extra lift force at the tail will create a nose up moment for the aircraft. So upward elevator deflection means delta E is going to be what? Delta E is going to be, upward deflection is what? Negative, right? So negative 30 degrees. Delta E is going to be negative. So it's not plus minus 30. Many students were writing plus minus 30. When we are talking about the forward center of gravity limit, delta is negative. So you see, to solve these problems, you need to have some conceptual understanding also. You need to have a physical understanding of what is going on. So we have, okay, I'm just going to copy this equation. We have CmCg equals to Cm0 plus dCmCg dCl Cl plus Cm delta E delta E. Now we want to trim the aircraft, right? So even when the center of gravity is at its forwardmost location, the idea is to trim the aircraft. So the overall moment coefficient will be equal to 0. So this is equal to 0.05 plus, now we need to recompute the value of the moment slope, because the center of gravity will now be in its forwardmost point. So we will substitute here later on. And in this situation, CL equals to 0.9. So that is also provided. Plus Cm delta E is minus 0.01 per degree. And delta E is minus 30 degrees. It's not plus minus, it is minus. Okay, so let's try to find the correct expression for the slope of the moment coefficient. To do that, you need to compute the neutral point. So you have dCm dCg dCl equals to xCg over C minus xNP over C. Now in the given condition, when xCg is equal to, when xCg equals to 0.3, this slope is minus 0.1. So 0.1 equals to 0.3 minus xNP over C. So we have xNP over C equals to 0.4. Okay, so this means we can write the slope of the moment coefficient with respect to the lift coefficient is equal to xCg over C minus 0.4. So this will have to be substituted here. So you get 0 equals to 0.05 plus xCg over C minus 0.4 times 0.9 plus 0.3. Okay, so this will give you 0.3. And now you solve for xCg over C. So you see, it matters whether you put a minus or a plus here. If you mess up the sign there, you will not get the right answer. Okay, let's calculate this. We get xCg over C minus 0.4 equal to minus 0.05 minus 0.3 divided by 0.9. So xCg over C equals to 0.4 minus 0.35 over 0.9. So this is the forwardmost location of xCg over C.